thing is called softcom something, right? So you see it's in Taiwan. Yeah. So everything is here. Okay. So that's in softcom. You can know it if you want. Alright. So I showed you several things. So let's repeat on the statistical side. We have seen this very hard and very high-dimensional problem of fitting the interbipolar surface. We have found this TSFM, dynamics and parametric factor model, that gave us these factors that we can analyze now in a parametric fashion. Macroeconomic bar analysis is one possibility. Another possibility is skew hedging. That means that you hedge its particular barrier options with respect to skewness effects. This was a talk that I gave in Kaohsiung last Friday. It was a little workshop on statistical risk management and applications. Then we have seen that the fast Fourier transform is a nice instrument technique, but concentrate on evaluating this risk neutral expectation. That means an integral that we approximate for nice Weber functions with Fourier transform techniques. Now let me come to the next two topics of this talk. This is risk management based on age distributions and adaptive volatility estimation. And then, last topic that we'll talk about skews and kurtosis droplets. Now, if you calculate value at risk, usually day per day analysis, you often apply normal distribution, but if you do that, say you standardize your residuals, either by gauge or by the method that I will show you, is the Wolfgang method. You standardize the residuals. That means you have the return of portfolio, you have an intertemporal variation, intertemporal volatility. You divide by the model prediction of this volatility, so say the gauge prediction or the gauge model. And then you should have normalized IIT variance. Yes? Okay, I'll show you. I like fluids, as you know, so I'll show you another film that makes this clear of a talk that I gave yesterday. First, I'll show you what I'm talking about. This data has been prepared by Chun-Ho Chen. You see over 5 years, you see development of DAX values. And suppose now you have a portfolio, that means a linear combination of these. So I'm very much interested how this portfolio varies over time. And one method is to look, first of all, at the variation of the covariance matrix of the returns. Yeah? So let's do the following. Let's take at each time point, you go back 1 year, this is industry standard. You go back 250 days, and then you calculate the 20-dimensional, because it's 20-dimensional terms, you calculate the 20-dimensional correlation matrix. Okay? If the data were normal, then by applying the Mahalanobis transformation, that means calculating sigma to -1/2 and multiplying the time series then, you would get roughly a time series that is quite nice. If so, let's look what we're doing. So here you see the correlation correlation matrix. You see the correlation matrix of the log returns of this data set over these 5 years. You see how it varies. You see sometimes one entry becomes dominant, there's no correlation with others, right? Okay. Also, this plot is studying explore, by the way, right? Everything we study is explore. Okay. So this is the correlation matrix, and now let us apply. So this, I don't want to wait over 5 years here. Now let us apply the method that is advocated by risk matrix. That means we take now this correlation matrix, calculate its eigenvalues, eigenvectors, and then we calculate the square root of the eigenvalues, the inverse, and we get the sigma to the -1/2. Right? Mahalanobis transformation. Okay. Now let's have a look how this looks like. This is the first. This is sort of the covariance, the correlation of the corrected 10-dimensional, 20-dimensional transfer. So it's much less. If I can show you parallel, maybe color code is of course identical. You see, there's much less color in there. That means we have some sort of correction has been done, right? But now let us look at, maybe I should move this one over here. Now let us look whether our correction was any good. Yeah? We look now at the correlation of the squared corrected time series. Yeah? Okay, so here you have the original one. Yeah? You write it all simultaneously in a second. Okay, so let's run the original one. Here you would run. Then you correct it. And then you look at the fourth moment, the so-called co-kurtosis. And you see there are the bad news. The color in here is often more intense than in here. So if this one, after correction, corrected for the first two moments, right? So approximately 0, uncorrelated. In the fourth moment, co-kurtosis, you still have a lot of structure over time. Yeah? And this is reflected. By the fact that a normal distribution, after correction, a normal distribution does not fit the tails or the middle very well. You can see it here from the log normal distribution. You see here, I take the log density here, so it's parabolic on the normal, but you see the tails here are much heavier than it should be under the normal distribution. So this model that we looked at here was RT is equal to sigma t epsilon t, RT the log returns, sigma t the volatility, for example, this portfolio of the 20 DAX values that you saw there, epsilon t identically distributed stochastic terms, and we just saw that epsilon t normal 0, 1 does not fit very well. And now this effect, epsilon t being normal does not fit very well, that occurs in stochastic volatility models, it occurs in gauge models, and of course also in arch models. You don't get rid of that. But what we propose to do here is to take another family of distributions, namely the generalized hyperbolic distribution family. It can very well replicate the distribution observed in financial markets. So this hyperbolic distributions or generalized hyperbolic distributions generalized in finance by Eberlein and Keller, and by Eberlein, Carlson and Christen, and an adaptive volatility estimation. That means a time-varying homogeneous approach to volatility, but based on the normal distribution, was developed by Mercurio and Spokoiny. And our idea in this paper, with Sokoyong and Yin Chen, was to combine A and B. That means combine generalized hyperbolic distributions with adaptive volatility estimation. Now, how do generalized hyperbolic distributions look like? Generalized hyperbolic distributions look awkward. They involve a so-called modified Bessel function of the third kind with some index lambda, but they have some nice properties that you will see in a second. So the hyperbolic distribution where this all came from has lambda equal to 1. The generalized term comes from varying lambda, looking at lambdas different from 1. For example, the normal inverse Gaussian is lambda equal to -1. The four parameters mu, delta, beta, and alpha can be interpreted as trend, riskiness, asymmetry, beta is a stimulus parameter, and the likeliness of extreme events. So alpha is the sort of correlate with the fourth moment. Here's an example for FX rates. So you take the FX rates of US dollar and Deutsche Mark, I think in this case. You standardize the returns. That means you divide FX rate return, you divide it by sigma t, either from Garch or from this model that I will show you. Then you try to fit to this density a parametric family. You saw the normal doesn't work very well, but you see here the hyperbolic distributions seems to fit extremely well. And I give you here the parameters alpha equal to 174 beta, etc. Okay, but now let me explain you so-called adaptive volatility estimation. This is a new paradigm that will revolutionize econometrics very soon because we have more and more data, and with more and more data, we believe less and less in stationarity. Do you agree with that? Do you believe in stationarity for very long time periods?
But actually, I like this field right here.
Okay, which field are you? I can also ask a question for your field. But you know what stationarity is, right? Stationarity means that you stick to one model all your life. Yeah? Long time period. Okay? Now, as I said, this will revolutionize econometrics because these ideas have now been developed in statistics quite well, and they are going into econometrics or financial econometrics. For example, this paper, first paper on adaptive volatility estimation, has been published by Spokoiny and Helmut Herberts and myself in Financial Econometrics in 2003 already. And here I talk about adaptive volatility estimation based on H and H distribution. So the idea is to say we are sitting here at a time point t or tau, and then we ask ourselves, if I go back m points, how big should m be so that I can safely say volatility is constant, or almost constant? Yeah? So that I safely estimate volatility, I have to use the mouse here, so I can safely estimate volatility as an estimate of the squared returns over this interval. Yeah? Okay. So again, adaptive volatility estimation asks this question about adapting a local interval of which I can assume a certain parametric model. It's nothing else than local parametric estimation at the right boundary point of the time. So you could also ask, how big has M to be to justify that the Garch model parameters are constant? Right? It's like asking, are there structural breaks in the data? It's the same question. Okay? Structural breaks, here it is. This is a so-called load check procedure that I present to you here. You 1 tau minus n. To check whether it is constant, you calculate, if it's constant on tau minus 1 to tau minus n, then it must be constant on every subinterval, on this one and on that one. Must be constant on every of these subintervals. Okay? Now, this is the basic test idea. To test is the volatility calculated on the left interval and the volatility calculated on the right interval. Is it almost zero? Is it almost the same? There are several ways to test this. You could set up a divergence, that means a likelihood ratio test, or you could just calculate this distance, but you have to calculate this critical value tau I, a statistical term. The critical value tau Ti. This one has to be calculated in Ti, and this doesn't work out. This Ti has to be calculated. Yeah? This is the whole difficulty to calculate this Ti. I'll show you a few tricks that you have to use there. The volatility is given as sigma t times epsilon t. Yeah? I'm doing the volatility estimation by estimating sigma t, but I have to determine the length of this interval. Okay? And for the length of this interval, I transform my returns with the parameter gamma. So I take the absolute returns to the power of gamma. Okay? If I do this transformation, I see that the absolute returns here to the power of gamma, this is a random variable, is connected to the volatility, also power of gamma, plus some random term. Yeah? If I do that, that allows me to take an average of these over a test interval I, take an average of these. Yeah? I can calculate its expectation, calculate its variance, and then I have the difficulty, the real difficulty with it is to prove that the GH distribution, the generalized hyperbolic distribution, has or fulfills such a tail condition. That means the GH distribution decays fast enough exponentially. Unfortunately, this is the case. So, in fact, it is so that the GH distribution has a lot of advantages relative to the Pareto distribution, for example, the T distribution. The Gaussian distribution goes down like, in the density goes down like, log density like e2 minus u squared. And the GH distribution goes down like e2 minus u, or u not u squared, u multiplied with a factor that goes to infinity, but it's eaten up by this exponential term that makes this inequality fly. And this inequality guarantees us that we can say the probability that theta I nickel minus theta tau, this is the corresponding supposed constant value of the transformed residual, is greater than the local bias. No, sorry, this doesn't work anymore. This is the local bias and the variance, and this becomes very asymptotically very small. That means under homogeneity, when I have the right interval, the local bias will be small, so the test can be done by looking at the local variance. Yeah? And I am looking at this local variance. I should show you maybe a picture from a different talk to make this more clear to you, namely from this work with with Liu Chen and this is not it, sorry. Where is it? Chen, that's it, this one. Okay. So let me here also show you a film. I like these films, as you know. Keep on showing you films. So here you see how this method would react. So sigma is constant here, this is the estimated sigma. over 200 simulations, and then it comes to this break point, so sigma jumps, then our interval becomes very small, and therefore the sigma estimate will also go up drastically. It stays constant again, and then it comes down. So this is the estimate of these critical values that I calculated for 200 simulations. And I wanted to show you how the tails taper out, the same plot, how the tails taper out for the energy distribution, for example. So here you have the quotient distribution, here you have the Laplace, which is more or less like the hyperbolic distribution, the energy, and the normal distribution. So this is the relative position of the tail behavior. And what I wanted to show you was this plots you have seen. I wanted to show you the estimate once more. This is very mathematical, I'm sorry for that. Here's. Okay. This is a different simulation, right? So even smaller peaks, like here small jumps of volatility or downgoing volatility are nicely detected by this method. Okay? Now, let me apply this now, for example, for D-mark US dollar exchange rates. This is what you get here. You see D-mark US dollar exchange rate looks very much like a gauge process. Yeah? So at each time point, I determine the interval back of local homogeneity or local constantness, and then I just calculate the squared. I just calculate the squared returns in this interval. Now, how do you estimate the value at risk? What you have to do is you have to find the quantile of the corresponding epsilon distribution, because you just multiply by sigma t at each time point t. So this is the quantile of the corresponding epsilon distribution, this one here. Quantile of the epsilon distribution. Yeah. And you estimate the scale here, of course, by an adaptive model. The QP is, as I said, the quantile of the epsilon distribution. We have seen very good fits for the hyperbolic or the energy distribution. That's why we stick to either hyperbolic or energy. So here you see the hyperbolic quantiles over time for the fx estimation, and you see the quantiles vary over time, and now you have to check in practice, you have to check how many points are lying outside these quantiles. You do this in back testing, or you can compare it with the normal model, for example. Here you have for 5%, here you have for 1%, you have here the FX data. This is D-mark US dollar data here. Lots of data, right? So 10,000 data points over, no, sorry, it's not 10,000 data points, I'm lying, it's 2,500 data points. And this lower quantile at each time point varies, and what you are doing is you are counting the number of outlying points. You can see this point out there? The points outlying, yeah? The outlying points, they should be either 5% or 1%, or actually this is a 0.5% or 1% of the whole data set that you have at hand. So now, to see whether this is the case, you do so-called back testing. Back testing means that you count the number of points that are lying outside the confidence intervals. You check how close they are to the desired proportion of exception, say 1%, 2%, 5%, or 100%. Yeah? There's in New Orleans book, you find a book test based on likelihood ratio, and if you do that for the normal model, going down from 5%, this is 5% here, down to 0.5%, you see that the normal model is strongly rejected, especially after 5%. It does not hold the desired significance level and indicates the rejection of the model, and the hyperbolic does extremely well as far as the position of the desired testing bar is concerned. Okay, now I would come to the last part of this talk. It's about stimulus.
I have a question.
very arresting. Some people consider extreme distribution, like Pareto distribution, is less extent to the model.
No, that's what I just said. No, completely different. I mean, I gave this workshop in Kaohsiung last week, showing the extreme value distribution. This is one approach. But there you assume that you have extremely thick tails, Pareto. The problem though is you can very hardly estimate these tails. It's very hard to estimate these tails. The Hill estimator is extremely variable. The peak over threshold estimator is not the solution, it's also extremely variable. And that's why you have always to be a little bit cautious when looking at extreme value distributions. Here you have a distribution that you can steer between normal and Cauchy, because you have essentially x to the power of lambda times e to the minus x, that's the speed of the tails. So by making lambda big, you can bring it closer to the Cauchy, that has heavy tailness, or closer to Pareto. And by making lambda smaller, lambda equal to 1, you bring it closer to the normal. You have more flexibility in this class. And still, you can prove a lot of theorems because essentially you have an exponential decrease of the density. Okay, let me come now to squares and kurtosis traits. Here again, you see this expected value, discounted expected value of the future payoff with the original density, European put and European call, and Q of ST is the state price of the underlying. In the Black-Scholes world, of course, this Q is not normal and unique. In the complete the arbitrage field, complete market model exists only one, but we will try to set up to say we are in an incomplete world and try to think of two SPDs, two state price densities, two state densities, and then compare two different models and trade initiate on these models. So basically, suppose one guy, one person has a certain utility, of course, that corresponds to this risk density, to correspond to the red curve G star. This is risk density G star. Another guy has the blue risk density F star. Okay? Now suppose you have this payoff, here's the payoff of a call. You see what happens in the tail of this call. The red guy, right, has a higher probability because his density is here. His density here is above the blue guy. Okay? So the red guy, suppose F is the one that you see on the market, but the red guy, because he has this utility, he will think these guys are cheap, so he buys these calls. This is called the skewness trade. Okay? So the tail situation is as follows: the red guy has, as I said, a higher option price for his call than the blue guy. Okay? So if the call price is priced using F star, then from the point of view of the G guy, they are too cheap. That means he will buy this call because he himself thinks there's a higher call. Essentially, analogously, you can also short a European out of the money put with striking. Now, this was skewness trade. Now, another payoff for the skewness trade called risk reversal has this structure where that is used, for example, for kurtosis trades. So in both cases, in both sides, here and here, you have higher prices for the blue curve than for the red curve. So here you would sell your call and you would sell your put on this side. Okay? The corresponding payoff profile is given here. Okay, so now we'll try to calculate two different SPDs. One is based on an option implied SPD, that's the option markets F star, option implied state price density, and this one we compare individual. To do that, we use Ball and Katucci's implied binomial tree algorithm, also used in Explore, of course, to estimate F star. And G star is inferred from a combination of non-parametric estimation of historical time series ducts and risk total forward Monte Carlo simulation. Okay, so implied binomial trees, they are, maybe there's a link down here, there's a link, you see. Implied binomial trees, Derman-Kani's implied binomial tree, can be calculated wrongly from this old talk. We have this in Explore, of course. Implied binomial tree is called IBP-decay. Let me show it to you. IBP-decay, here it is, implied binomial tree. So here it calculates you for a certain molar function, it calculates here the implied binomial tree. Maybe I have there's also this thing called nice tree. Nice tree, maybe nice nut. This one, nice nut. That makes this implied binomial tree a little bit nicer. See, then it looks like this. You know what an implied binomial tree is, by the way? Implied binomial tree, option pricing structure. The implied binomial tree will estimate you the SPD. This is Derman-Kani and Barlin-Capisi's algorithm. It essentially looks like that. I'll show you how it looks like here. As an example. Okay, so I take the implied molar smile, here again from October 2000, just a different way to show it to you here. And the implied binomial tree is calculated as follows. You see the implied molar smile, right? This is here, an example. And then you start with 100, then you calculate in this tree, you calculate the development of the stock always so that you get the correct smile structure that you have in your implied volatility that you observe. And so here, at this point out here, you get the future stock prices. And you get the future transition probabilities, and you get the error de Broglie prices, lambda Ni. So this lambda Ni's, they are, this is the tree of the error de Broglie prices here, they are nothing else than the risk total density, discrete approximation of risk total density, multiplied with e to the r tau. The total time to maturity, in this case 1/4. So the SPD is nothing else than this here. Right? This is the SPD. Now let us look at the way how we make this forward simulation. We do this by taking a so-called local volatility model. This is the geometric boundary motion. We have a local volatility model. That means volatility is a local function. It depends on st and t. And every Brownian motion rate is multiplied with this local volatility term. This model, the so-called Dupere model, is very, very closely connected with the implied molar surface. And in fact, the implied molar surface dynamic will influence the sigma t. Okay? So I told you for the SPD you take the error de Broglie prices, you multiply them with e to the r tau, you get f star. And how does this look like? Let me show you. Okay. Let me show you how it looks like here. So our setup is as follows. We take from 24th of March 97 to 23rd of June 97, this is about a year. If you look ahead 1 year, so here we see at this time point, we are here at this time point. At this time point, we see the option pricing structure for a quarter of a year ahead, 3 months ahead. From this option pricing structure, we take an IBT, implied binomial tree, and approximate this implied binomial tree, approximate its f-star function. Then I take option data 2 weeks back, this is the historical approach, and here you see the SPD for 10 time steps, quarter of a year ahead. And then I take the option data 2 weeks back and estimate historically this function sigma, this local volatility model. Yeah? It is the local volatility model by Dupier. Then, fortunately, in this local volatility model, if I go, because here I estimated under the objective measure, I can use Gazzano transformation and I can use the risk interval, but in the risk interval, fortunately, sigma will not change. The drift is adjusted, but the diffusion function is identical in both cases. How do I estimate this sigma? The sigma is estimated by a theory that I have developed with Zubakov, 1979, and by Florence Leroux. You take the square differences of your stock and you use a Knoll estimator, and when you do that, sigma will look like these functions that you see here. Then you simulate them ahead with this Wheelstein scheme. We are using the so-called Wheelstein scheme. Then you simulate many, many paths to get the density G, right? So finally you have density G for the log returns. And when you do that, then you get this density G, yeah, based on the econometrics point of view, say, but it's a risk interval G with a given sigma that you estimated from the past. Here you have such an estimated G for example, for the 19th of September 97, based on estimates 2 weeks prior to the 23rd of July 1997. 10,000 paths is simulated. Okay? Now we do a comparison of the implied and the time series SPD. So F star here is the triangle, the standard deviation of the blue curve and the red curve are given here. They are closely together. You can see the skewness, as I predicted. The skewness is different. The skewness, in most cases, the skewness parameter of F star is below the skewness parameter of G star, which gives rise to this skewness and kurtosis trading. The same is true for the kurtosis. Now let's set up a trading strategy. The question is now, is it possible to exploit this SPD comparison by means of skewness and kurtosis trades? And is the strategy performance consistent with SPD comparison? Now, to set up a skewness and kurtosis trade, I look at short puts and long calls. I have explained it to you. Very simple payoff profile. For the kurtosis, I have to use this butterfly profile. So I have a little bit more complicated data structure here. Then I look at the performance measurement. I look at the returns for each of the 23-month period measured by the portfolio return. And finally I get the following table for the skewness trade. I have in June 1997, when I start, I have 541 euros. Then I have a cash flow of 37, so net cash flow is 579. So when I do that, you can see that I'm happy. Sometimes I lose money with the skewness and kurtosis trade, but at the end I'm coming up with a positive cash flow here. Unfortunately, when I extend this to March 02, that means I go 2 years further, or 9/11, for example, which happened exactly, of course, here in this net cash flow. Then I have lost a lot of money. So you can see also here on the DAX evolution from 1997 to 2003. You see this DAX evolution reflects 9/11, which is here, and the other events like the Russian crisis, etc. Let's now look at the kurtosis trades. The kurtosis trades also turn up to be negative. So the conclusion is that the trading performance is positive before it comes to a shock, yeah, like in 2000 or 2001, and we have unfortunately negative performance in the years from 0 to 2002. And here I give you a few references for this paper, and I would like to thank you for coming to this Herbert Simon lecture. And this is the first part, I understand. Tomorrow is another part where I talk about pensions, lotteries, and measuring statistical risk on financial markets. And there I will talk about extreme values, if you want, in some comparison. And I'm looking forward to see you tomorrow. Thank you very much.
Any questions? No questions? Okay. Thank you for Professor at today's lecture. I think this lecture will be helpful to our research. Thank you.
Thank you.